maximum voltage that can appear on a transfer switch for a 480 volt system is 640 volts. This overvoltage condition can arise due to a number of factors related to the interaction between the utility power, the generator, and the transfer switch itself. Understanding these factors is crucial for ensuring the safe and reliable operation of the electrical system and preventing damage to equipment. Firstly, consider the role of the transfer switch. Its primary function is to switch the electrical load between the normal power source, typically the utility grid, and an alternate power source, usually a generator. This switching action, however, can introduce transient voltages into the system. These transients are short-duration voltage spikes that can significantly exceed the nominal voltage level. Secondly, the generator itself can contribute to overvoltage conditions. Generators are designed to maintain a relatively constant voltage output, but their voltage can fluctuate under varying load conditions. Factors such as the generator's voltage regulation system, its response time to load changes, and the characteristics of the connected load can all influence the generator's voltage output. Furthermore, the impedance of the generator and the utility source play a significant role. Impedance is the opposition to the flow of alternating current and includes both resistance and reactance. When the transfer switch operates, it effectively connects two sources with potentially different impedances. This impedance mismatch can lead to voltage reflections and oscillations, which can manifest as overvoltages at the transfer switch. Another critical aspect is the presence of inductive loads in the electrical system. Inductive loads, such as motors and transformers, store energy in a magnetic field. When the current through an inductor is interrupted, the stored energy can be released, resulting in a voltage spike. The magnitude of this voltage spike depends on the inductance of the circuit and the rate of change of current. During the transfer switch operation, inductive loads can generate significant voltage transients that contribute to overvoltage conditions. Capacitor switching can also introduce overvoltages in the power system. Capacitors are often used for power factor correction, which improves the efficiency of the electrical system. However, when capacitors are switched on or off, they can create voltage transients. These transients are typically of short duration but can have high amplitudes, potentially exceeding the voltage rating of equipment connected to the transfer switch. The grounding system also plays a vital role in mitigating overvoltage conditions. A properly designed and installed grounding system provides a low impedance path for fault currents to flow back to the source, helping to limit voltage rise during transient events. An inadequate grounding system can exacerbate overvoltage problems and increase the risk of equipment damage. Surge protection devices, or SPDs, are essential components in protecting electrical systems from overvoltages. SPD are designed to clamp voltage levels and divert surge currents away from sensitive equipment. They are typically installed at the transfer switch and other critical locations in the electrical system to provide comprehensive overvoltage protection. The National Electrical Code, or NEC, provides guidelines for the selection and installation of SPD. NEC Article 280 covers surge arresters, and Article 285 addresses transient voltage surge suppressors. These articles specify the types of SPD that are permitted, their installation requirements, and the performance criteria they must meet. Considering these factors, it is important to understand how the maximum voltage of 640 volts is determined for a 480 volt system. This value is often based on industry standards and engineering practices that take into account the potential for overvoltage conditions. It represents a safe operating limit that ensures the reliable performance of the transfer switch and connected equipment. The 640 volts value is not arbitrary. It is typically derived by applying a safety factor to the nominal voltage of the system. In this case, a 480 volt system may experience voltage fluctuations due to various factors, such as load changes and system disturbances. The safety factor accounts for these fluctuations and provides a margin of protection against overvoltage conditions. To calculate this, it might involve multiplying the nominal voltage by a factor, for example, 480 volts times 1.33, which is approximately 640 volts. This safety factor can vary depending on the specific application and the characteristics of the electrical system. The selection of a transfer switch for a 480-volt system should consider its voltage rating and its ability to withstand overvoltage conditions. The transfer switch should be rated for a voltage that is higher than the expected maximum voltage in the system, including any potential transients. This ensures that the transfer switch can operate safely and reliably under all operating conditions. Regular inspection and maintenance of the transfer switch are essential for preventing overvoltage problems. Inspection should include checking for loose connections, damaged components, and signs of overheating. Maintenance activities should include cleaning the transfer switch, lubricating moving parts, and testing its operation. Addressing these potential issues proactively helps prevent future problems. In summary, the maximum voltage that can appear on a transfer switch for a 480-volt system is 640 volts. This overvoltage condition can arise due to factors such as switching transients, generator voltage fluctuations, impedance mismatches, inductive loads, capacitor switching, and grounding system deficiencies. Understanding these factors and implementing appropriate mitigation measures, such as surge protection devices and proper grounding, is crucial for ensuring the safe and reliable operation of the electrical system. Also, NEC Section 700.12. B6 addresses the issue of overcurrent protection for emergency systems, where generators are often used as an alternate power source, and 700.12. E discusses the requirements for transfer equipment. NEC Article 701 deals with legally required standby systems, and NEC Article 702 covers optional standby systems. Each of these articles contains provisions related to transfer switches and their operation. Let's further explore the technical aspects related to overvoltage protection in transfer switches for 480-volt systems. One important consideration is the insulation coordination of the electrical system. Insulation coordination refers to the selection of insulation levels for various components in the system to ensure that they can withstand the expected voltage stresses. The insulation coordination should take into account the potential for overvoltages and the characteristics of the surge protection devices used in the system. The withstand voltage rating of the transfer switch is a critical parameter that must be considered. The withstand voltage rating specifies the maximum voltage that the transfer switch can withstand without experiencing insulation breakdown or other damage. The withstand voltage rating should be higher than the expected maximum voltage in the system, including any potential transients. Another relevant standard is ANSI C62.41.1 and ANSI C62.41.2, which define surge voltage waveforms and test methods for surge protection devices. These standards provide a common basis for evaluating the performance of SPD and ensuring that they can effectively protect electrical equipment from overvoltages. IEEE Standard 1100, also known as the Emerald Book, provides recommendations for power and grounding sensitive electronic equipment. This standard covers various aspects of power quality, including overvoltage protection, and provides guidance in the selection and installation of SPD. The type of surge protection device used in a transfer switch depends on the specific application and the characteristics of the electrical system. Some common types of SPD include metal oxide varistors, or MOVs, silicon avalanche diodes, or SADs, and gas discharge tubes, or GDTs. MOVI are the most widely used type of SPD due to their relatively low cost and high energy handling capability. SAD offer faster response times than MOV but have lower energy handling capability. GDT can handle very high surge currents but have slower response times than MOV and SAD. The location of surge protection devices in the electrical system is also important. SPD should be installed as close as possible to the equipment they are intended to protect. In the case of a transfer switch, SPD should be installed on both the utility side and the generator side of the switch to provide comprehensive overvoltage protection. The grounding system plays a critical role in the performance of surge protection devices. A properly designed and installed grounding system provides a low impedance path for surge currents to flow back to the source, helping to limit voltage rise during transient events. The grounding system should comply with the requirements of the National Electrical Code, or NEC, and other applicable standards. The NEC specifies the minimum size of grounding conductors and the methods for grounding electrical equipment. In addition to surge protection devices, other measures can be taken to mitigate overvoltage conditions in transfer switches. These measures include using shielded cables, installing filters, and implementing proper grounding techniques. Shielded cables help to reduce the amount of electromagnetic interference that can enter the electrical system. Filters help to attenuate high-frequency voltage transients. Proper grounding techniques help to minimize voltage rise during transient events. When selecting a transfer switch for a 480-volt system, it is important to consider the manufacturer's specifications and the results of independent testing. The transfer switch should be certified by a recognized testing laboratory, such as Underwriters Laboratories, or UL, or Intertek, to ensure that it meets applicable safety and performance standards. The transfer switch should also be tested to withstand the expected overvoltage conditions in the electrical system. In summary, overvoltage protection in transfer switches for 480-volt systems is a complex topic that requires a thorough understanding of electrical engineering principles and industry standards. By implementing appropriate mitigation measures, such as surge protection devices and proper grounding, it is possible to minimize the risk of overvoltage damage and ensure the safe and reliable operation of the electrical system. The 640 volts maximum on a 480-volt transfer switch represents an upper limit to prevent equipment failure and ensure safety.